So we're going to talk about models and modeling a lot in this class. As you know, our main book for Quant Book Club is The Model Thinker. And even when we're not explicitly talking about a model, which we will do a lot, looking at regression and other linear models, generalized linear models like logistic regression, even when we aren't explicitly using a model, we are often relying on some kind of implicit model. And we'll explore that over the course of the class. Generally, it's going to involve some sorts of assumptions that we're taking into the examination of data. So what exactly is a model? Normally, if I weren't recording this in the solitude of my own home, I might ask people to give some examples of models, and sometimes outside of statistical models, you may think of things like a toy model boat, or a map as a kind of model, and actually thinking about models as sorts of maps in a general sense can be helpful. What is this? If I ask you what that is, many people will say cat. Maybe occasionally someone will say dog, although the pointy ears somehow seem to be symbolic, at least for many of us, of a cat. It's a very, very simple model, but it symbolizes in some way a cat, something about the structure of the picture, even though it's a simple stick figure with just the exception of the head, maybe the curvy tail. Clearly not a cat. Then again, if I showed you a photograph of a cat, we could say that is a sort of model. It's a sort of indicator, a pointer to the concept of a cat, but is also still not a cat itself, right? It's a photograph of a cat. So more of the elements there's more verisimilitude, as it's sometimes said. There's maybe it's closer to the actual cat than this model is. Here's a model train. As I mentioned in our first meeting, it's not exactly true, although it's to say that a model train is false. When we talked about models being false, it's a little bit of a stretch to think of models being true or false, and so we should really be thinking about models, whether they're useful. I guess what you might say for a false model is a model that's not useful for anything, and so we want to think about whether a model is a good model. We want to think about it's not just a model. That models can't just be good in general, although they may be generally good in the sense that there are various uses that they can be put to. There can be sort of Swiss Army knife models, but generally we want to think about what the purpose of a model is, right? So, this cat model there is not useful for much of anything other than to maybe win a game of Pictionary, where the word is cat that you're trying to communicate. The train, what ways we can think about is that a good model. Hopefully there may be some structures that are stand-ins, simple stand-ins for the real thing. You'd want the scale to be accurate, right? So you'd want, for example, if the height was to one scale and the width or length were to different scales, it would be a much worse model. And we could talk about in what sense it is representing some aspects of trainness and not others. A model train could sit on your mantle and not move. It would still be a decent model of a train if perhaps maybe even more intricately designed than this train here. If you had a train that also can move and go around a track, but maybe doesn't look as much like a train as the one that's expensive and sitting unmoving on my mantle. They're both good in different ways. One is visually more similar to a real train, and the other one captures the movement in a way that the one that sits on my mantle doesn't. So always be thinking about this is the analogy to statistical models of behavior or social life are also going to be better for some things and worse for others. Here's another model. It's a model of a condo or an apartment, and it doesn't look in a lot of ways like the apartment itself. but this model is good at showing the sizing of rooms and the locations where they are with relation to one another, the overall size of the apartment, the location of entryways, and some important structures like the kitchen cabinets and appliances, where a table can go, and some similar things for bathrooms, right? But a lot of elements are not. We might say, oh, I want a better model. A better model is going to give me more of the elements. Maybe is it right to say it's a better model if I also show that I have a bunch of laundry on the floor in the master bedroom, right? It may capture my apartment, more details of the apartment, right? But I might not want that for a lot of purposes. Like, let's say I'm thinking of selling it, and I might not want to include the details that aren't relevant for that buyer. The buyer doesn't need to know that I keep laundry on the floor of the bedroom right now, even though it is true in some sense, right? I could do a three-dimensional rendering of this, but maybe it's too complicated and not as useful to people. They can't put it in their pocket, so it's not useful in transporting it somewhere either. Subways are interesting. Different sorts of maps that capture different aspects of reality for different purposes are interesting. So subway maps have particular goals they're trying to optimize. One of them is to make sure that you can see the individual stops and where they are in relation to one another. When you overlay them on a map of like a sort of typical city map, sometimes they aren't as great because we're trying to make sure that they're all spaced out evenly so one can find all the stops. So if you have a bunch that are close together and a bunch further apart, those differences in lengths might not always be represented. And in some ways, you could say, oh, that's not a very good map. Took me 10 minutes to go 5 stops, and then it took me 30 minutes to go the next 5 stops, and I didn't expect that based on the spacing. Well, that wasn't the purpose of that particular map, so it's really important to know what a model or a map is supposed to be used for and what it shouldn't be used for. So again, this idea of models being right or wrong, the famous quote by, I think, well, it's usually attributed to Dr. Cox, I think, is that all models are wrong, but some are useful. I've heard others update it to say that the question of whether a model is right or wrong is not really meaningful. In the same way that you wouldn't typically, you wouldn't typically look at a toy model and ask if it's wrong. I mean, I guess you could say certain things are not capturing a reality in the way that you want, but it's hard to say whether it's right or wrong in a vacuum. It's never the thing it's trying to model, right? It's never exactly that thing. We wouldn't want to model a map of our state that was the size of the state. And so the question of whether it's useful is what's important, and you can't ask in sort of a vacuum. You need to know what the purpose is before doing so. Right, so the question of whether which model is better, this is really something to keep in mind, because typically in data science, we get into this mode of comparing models and thinking there is some universal answer to which one is better, especially in computer science, data science, where it's typical for the goal to be very specifically prediction. You can clarify that you want out-of-sample prediction or external validity in certain, with new data, that's fine. But within social science, prediction is important. In using a model, you don't want a model that can't predict at all, but oftentimes when we're deciding among different modeling techniques, we might sometimes prefer one that doesn't make as good predictions, makes decent predictions, but is more interpretable. So there are different, in model comparisons, we have to think about what we want to use it for again, and prediction is only one thing, as your textbook describes as well, Gelman and company. So we got to think about what models do and why do we use them. They're means of abstracting. They retain relevant aspects of a phenomenon for a task at hand. And sometimes, in fact, a simple model that really emphasizes or brings out, reflects particular aspects, we don't want it to be realistic more realistic by including a bunch of other ones that aren't relevant to our task at hand. They allow us to do certain measurement of quantities of interest. Sometimes that involves, scaled versions, right? Like if we were talking about, toy trains and subway maps or other maps, we're actually talking about, spatial proportions. But in statistical and quantitative modeling, often we're using maybe certain proxy variables that stand in for certain concepts that we can't measure directly. Maybe we have a few imperfect indicators of the concept of anxiety or political efficacy, and we're using our model that, for example, that maybe these imperfect indicators they're being driven in some common way by the latent variable that's driving them. And models are going to allow us to make comparisons. So in a regression model, thinking about two different cases where with an X value, or let's say two different people with a year difference in their amount of education, and looking at how they compare in a number of different ways based on that difference, or looking at those who differ on one with respect to one variable. How do those individuals on average differ with respect to something else? And they facilitate systematic explanation in a shared language. We say, okay, we're simplifying the complicated social reality or behavioral reality to this kind of two-dimensional, one-dimensional. There's a level of reduction, an element of reductive quality in it. So, to avoid earning the epithet that we're just being reductive, we want to be explicitly reductive and explicit at what we're reducing, what we're leaving out, and that's actually one of the justifications that Scott Page gives in his book, The Model Thinker, for being a multi-model thinker, that we have different maps and we use them to sort of triangulate on various aspects of reality. So we want to think about what mathematical, statistical, computational models of behavior do. What do we want them to capture? What are good features for models to have? I'll leave that open to you as a question. You might think of nature or raw reality and all its intricate complexity and infinite kind of chaotic interaction as unfolding, and people are making decisions and nature is working in some way. I'm thinking of nature in the broad sense of raw reality. And we're going to try to capture that using some design and measurement strategy. And data in this context is the result of applying our measurement, applying our research design to the sort of raw unfolding of reality, right? We're getting these snapshots of data. And so we think of this process as a data generating process. That is to say, nature unfolding and reality just taking form is not enough. We are recording some aspects of it with all the limitations of whatever that recording process is, and we get data as a result. And in fact, in the context of statistical modeling and methods of capturing data quantitatively, statisticians often think of P of y, say y is a variable, and that y is distributed as P of y as itself generating data, but that is actually itself a model of a data generating process, right? A statistician may describe, say, a normal distribution or a normal y is being generated according to some normal distribution centered on a regression line. And then if we were simulating data creation, we would think of that underlying distribution as itself generating the data. So that distribution is a model of nature. And we think of that model as the stand-in for the process above, right? That itself, actually, statisticians often refer to distributions or likelihood functions as models. When they talk about models, that's what they mean. Example of a deterministic model might be that we have an outcome variable y, and we are saying specifically it is equal to some slope times x, another variable, plus a y-intercept. That equation for a line that you learn in algebra, coordinate geometry. That one above is purely deterministic. It's not very useful to us. On the other hand, a purely probabilistic model might say y has a certain distribution that's parameterized by some theta, right? So when we talk about male heights being normally distributed with a mean of, I forget what it is, 70 inches and standard deviation of 2.5 inches, we're giving that theta there is in that model is the mean and the standard deviation, the mu and the sigma. And we're thinking about the distribution being purely probabilistic, not being modeled, conditional on any other information. And typically, and this is sort of the heart of the basic models we encounter in this course, we try to break up sort of the systematic, or whether you think of it as deterministic or not. I typically don't, most social scientists don't, thinking of some component that is the pattern part, right, which you can think of as systematic. We can think of there being, we can model it as if there was a piece of data generating processes which are sort of determined by a bunch of other factors, and then basically partition the data generating process into that systematic part, which can be described, and the stochastic or probabilistic components, which can also be described in terms of their overall random tendencies. And so more simply, we could say that a variable y is distributed with some, it has some probability distribution that's conditional on the predictor. So when we think about a regression model as an outcome variable as some linear function of input variables or predictor variables, that can incorporate both of these components. And so, for example, thinking of y as a function of x, thinking of dependent variable as a function of independent variables. You don't often see it this way. Statisticians like to think of it this way to remind us, instead of it being a y is simply, beta plus beta naught plus beta 1 x plus some error. We can think of y's themselves as conditional on our x being normal, but with a mean centered on the regression line, beta naught plus beta 1x. If this is all new to you, we'll be encountering it over the course of the semester, so no worries. So yeah, that's it. So I'll talk to you again soon.